Greetings everybody, and today we're going to be deriving the Cauchy-Riemann equations. So Cauchy and Riemann, two very big names from complex analysis, so probably a very important set of equations, and they are in fact these equations that contain these partial derivatives here, and in fact you use the Cauchy-Riemann equations to test whether complex functions are differentiable at certain points. So over here I have written out a function f that goes from c to c, so complex valued function, and obviously f is going to take in some complex number z, but I've written z as x plus iy, so z has a real and imaginary part. And notice that I've written f in terms of its real and imaginary part. So the real part I'm going to call the function u. To be clear, is also a real function. And a v over here, that represents the imaginary part. V is also going to be a real function, and I should probably put R2 because we're taking in two real numbers, x and y, the real and imaginary parts of z. So if we can decompose f into u and v, the real and imaginary parts, we can take a look at their partial derivatives in terms of the real and imaginary parts of z. And that's how we can come up with the Cauchy-Riemann equations. And now we're going to take a look at how we can derive these equations. So remember I said that the Cauchy-Riemann equation tells us whether functions are differentiable at certain points. So let's take a look at differentiability. If you take a look at the real case, let's say we have a function f going from r to r, so just a real valued function. If f is differentiable at a certain point, that means that the limit of the difference quotients exists. So what do I mean by that? If we take a look at f of x plus some small change in x, and then we subtract off f of x, so this is the small change in the output of the function, and we divide this by the small change in the input of the function. If the limit over here as delta x approaches 0 exists, that means that our function is differentiable at whatever point x we choose. So we can extend this to the complex case as well. Let's consider now f going from c to c. If f is differentiable at some complex number z, that means if you have f prime of z, that should be equal to the limit. And now instead of having delta x going to 0, we're going to have delta z going to 0 of f of z plus delta z minus f of z, and we divide this by the small change in z, like so. Problem with doing this in the complex case is that taking this limit is a little bit ambiguous, because if you take a look at the real number line, so maybe this is the x over here, and we have some point x. If we take a look at a small change in x, well, that only can exist on this axis. So we can have a delta x this way or a delta x this way. But if you look at the complex plane, so now we're in 2 dimensions, so this is a z. If we have some point z over here, then a delta z could go in any direction. It could go over here, that's a delta z. It could also go over here, that's another delta z. It could be in any direction, and it's a little bit hard to pick which one. But what we're going to do instead is, instead of taking a look at just delta z, notice that delta z, we can look at it as both a small change in delta x as well as a delta y. So maybe we have a delta x over here and a delta y. And that's exactly why we want to take a look at all these complex numbers in terms of its real and imaginary parts. That way we can decompose these small changes into the small change along the real axis and the small change along the imaginary axis, and it's a little bit easier to talk about it that way. So instead of taking a look at z's over here, let's take a look at x plus iy instead. So if z is equal to x plus iy, I'm just going to write the limit here first. Then the first term will be f of x plus delta x plus I times y plus delta y. So that's exactly z plus delta z. We have these x plus iy is our z, and then we also have delta x plus I delta y, and that's our delta z. And then of course we're going to subtract off f of x plus iy, and then this is all divided through by delta z, but delta z is just delta x plus I times delta y. And notice we have the limit in front. We're no longer dealing with the delta z's, we're dealing with the delta x's and delta y's. So let's take the limit as delta x approaches 0 as well as delta y approaches 0 instead. Alright, and here what I want to do is I want to replace f of z in terms of its real and imaginary parts, in terms of the functions u and v. And if we do that, we are going to get the limit as delta x approaches 0 and the delta y approaches 0 of, now we have the real part. This is the real part of z, and then we also have this over here. That's the imaginary part of z. And if we replace f with its real and imaginary part, well, we're going to get u, the real part first, so that's going to be x plus delta x, comma y plus delta y, and then we have this imaginary part of f, so plus I times v, x plus delta x, and then y plus delta y. So all of this stuff over here, that's the first term. We're going to subtract off f of x plus iy, but that's exactly what we have over here. So we're going to have minus u of x comma y, and then minus I times v of x comma y, and then this is all divided through by delta x plus I times delta y. Alright, and now what I want to do, we have our u's and v's, all our imaginary parts and real parts mixed together. Let's try to separate them out a little bit. So if we do so, we're going to get the limit as delta x approaches 0 and delta y approaches 0. Let's take a look at the u's first. That's our real part. We're going to get u of x plus delta x comma y plus delta y minus u of x comma y, and then this is divided through by delta x plus I times delta y, and then we're going to add the imaginary part, which is our v function, but let's also factor out an I, and if we do that, we're going to get I times v x plus delta x comma y plus delta y minus v of xy, and then this is divided by delta x plus I times delta y. And remember, all this stuff is still equal to our f of z that we started off with. And now let's assume that these limits exist. If these limits exist, then obviously our f prime of z must exist as well. And notice one thing, we have the limit as delta x approaches 0 and delta y approaches 0. And we don't really want them to approach 0 together because that would be a little bit tricky to deal with. Let's see what happens as we take one to approach 0 first and then the other. So what do I mean by that? Let's rub out all of this stuff up here. We don't really need it anymore. So we just have to remember that all of this stuff is still equal to f prime of z. So let's see what happens as delta x approaches 0 first. So that's kind of like the first case, which is case 1, which is delta x approaches 0 first. If delta x approaches 0 first, then all these delta x's will literally just disappear off. And we're going to be left with f prime of z is equal to the limit as delta y approaches 0, because delta x is already 0, of u of x comma y plus delta y, and then minus u of x comma y, and then this is divided through by, now delta x is 0, we're left with I delta y, and then we're going to do the same thing over here. We're going to get plus I times v of x comma y plus delta y minus a v of x comma y divided by, now delta x is 0, we're left with I times delta y, and also the nice thing is these i's will cancel each other out. And notice, what do these fractions over here represent? They actually represent the partial derivatives of u with respect to y and v with respect to y. Because if you have a look at what's going on, we're only seeing what happens to our output as our y varies by a little bit. So in fact, what this gives us is, well, first of all, we have 1 over I, which let's replace that with minus I, of the partial derivative of u with respect to y, and then plus the partial derivative of v with respect to y. So that's what we get as we take the limit as delta x approaches 0 first. And now let's do the same thing for what happens if delta y approaches 0 first. So as delta y approaches 0, then a very similar things will happen. We're going to get that f prime of z is going to be equal to the limit as delta x approaches 0, because delta y will be gone, and then we're going to have u of x plus delta x comma y minus u of xy divided by, now delta y is 0, so we're just left with the delta x, And so over here we have I times v of x plus delta x. This should be a delta x actually. And then comma y minus v of x comma y. And then this is divided through by, now again, delta y is gone. We're just left with the delta x. And very similar to what we had before, both of these fractions are just looking at how our functions u and v change with respects to the variable x only. So this is going to give us the partial derivative of u with respects to x, and then plus I times the partial derivative of v with respects to x. Alright, and remember this is equal to f prime of z as well. And over here we've taken the limit two different ways, and we have to get our f prime of z out the other end. So what that tells us is that both of these expressions must be the same. So I'm going to write it as follows. Notice that partial u partial x, that's equal to the partial derivative of u with respect to x. Then we have plus I times vx, so partial derivative of v with respect to x, and this must equal to what we have up here. So I'm going to write the real part first over here. That's v with respect to y minus u with respects to y. And then we also have an I out the front. And notice this is a complex number, this is a complex number. If they're equal, that means the real parts are equal and the complex parts are equal. So that means that ux is equal to vy. And then over here, if we look at the imaginary parts, we have vx is equal to minus uy, or we can put the negative on the other side, and we basically end up with what we had at the start, the Cauchy-Riemann equations. So what does these equations tell us? Remember that they come from these difference quotients, and we took the limit as both delta x and delta y approaches 0, but in different orders. So for a function to be differentiable in the complex plane, and that goes for all multi-valued functions as well, in order for their derivatives to exist, they must approach the same value regardless of which direction you approach that point. And in this case we chose the direction along the imaginary axis and the real axis. In general you can pick any other two directions, but we picked the x and y directions because they were the easiest to work with. So if our function satisfies these equations, that means it's going to be differentiable at that specific point that we choose. And we're going to do a bit of an example now. We're going to take a look at some functions that are differentiable everywhere and some functions that are differentiable nowhere. So let's take a look at the function f of z is equal to e to the z, so the complex exponential function. The first step is to decompose e to the z in terms of u and of v, and that's not too bad to do. Notice that e to the z is exactly e to the x plus iy, and this is equal to e to the x, and then we have e to the I times y. But notice that over here, e to the I times y, we can use Euler's formula for that. That's going to give us e to the x times the cosine of y plus I times e to the x times the sine of y. So over here, we have our function u, and over here we have our function v. And we've figured out f in terms of its real and imaginary parts. Let's calculate these partial derivatives. So first of all, ux is equal to, well, let's differentiate this thing with respects to x. Cosine of y is just a constant, so that's going to stay. So we're just going to have cosine of y, and then e to the x, derivative of that is just e to the x. So that's ux, and let's calculate v sub y. Well, if we differentiate this thing over here with respects to y, e to the x is a constant that's multiplied out the front, so that stays. And then derivative of sine is just cosine, so we have cosine of y. And right away, notice that ux is definitely equal to vy. So our first condition is checked. And let's calculate u sub y now. So uy, let's see, we have e to the x, that's still out the front, and derivative of cosine is negative sine, so we have negative sine of y. And let's calculate v sub x. So v sub x is equal to, well, differentiating this thing, sine of y is just a constant, so let's leave that out the front. Derivative of e to the x is e to the x, and here we want negative, so let's put negatives everywhere. And notice that u sub y is exactly the same as negative v sub x, so the second condition is met. That means that no matter which x and which y we choose, so no matter which complex number we choose, our function e to the z is always differentiable, and we call those functions entire functions. And now for another example, we want to take a look at a bit of a strange function. It's the conjugate function. So f of z is equal to z bar. First of all, let's decompose this function into its real and imaginary part. That's pretty easy to do. That's exactly going to be x minus iy. So in this case, u of x comma y is going to be equal to just this real part, which is x, and then a v of x comma y is the imaginary part. That's going to be minus y. And now to calculate these partial derivatives, u sub x is going to be equal to, well, differentiating this thing, that's just going to give us a 1. V sub y is going to give us, well, this is going to be negative 1. U sub y is going to give us, well, that's going to be 0. And then minus a v sub x, well, differentiating, there's no x's over here, so the derivative of that is obviously a 0. And even though these two partial derivatives are the same, these two other partial derivatives are different. So even if one of these conditions aren't true, that means our function is actually not differentiable. And notice there's no x's or y's flying around anywhere. These are just constants. So for this function, conjugate of z, these equations would be independent of whatever complex number we choose. So what we can say is that the conjugate function is not differentiable everywhere. It's a non-differentiable function. So that's pretty much all I have for this video, just the derivation of the Cauchy-Riemann equations and maybe some examples to demonstrate how it works as well. So hopefully you guys enjoyed this video, and until next time, have a wonderful day, and I'll see everyone later. Bye bye.